This memo sheet is designed to consolidate everything you have learned so far into a single, clear, and actionable reference. You have already explored Git fundamentals, branch policies, pre-commit hooks, security concepts such as confidentiality, integrity, and availability, and the relationship between threats and the delivery pipeline. This document brings all of these pieces together into a coherent picture of what a minimal secure pipeline looks like in practice. What is a pipeline and why does security belong in it? A pipeline, in the context of software development, is the automated sequence of steps that transforms source code written by a developer into a deployed application running in a production environment. This sequence typically includes stages such as code writing, version control, automated testing, building the application, and deploying it to servers. Security must be embedded into every stage of this pipeline rather than added as an afterthought at the very end. The reason is simple. The later a vulnerability is discovered, the more expensive and complex it is to fix. A flaw caught during development costs far less than one discovered after deployment. This philosophy is at the heart of DevSecOps, making security a shared, continuous responsibility across the entire pipeline rather than a final checkpoint. The foundation. Git is a secure starting point. Git is the version control system at the origin of every modern pipeline. Every change to the codebase passes through Git, which means Git is both the first opportunity to catch security problems and the first point of risk if misused. Key security principles to remember about Git. Every commit creates a traceable, immutable record of who changed what and when. This traceability supports the integrity principle of the confidentiality, integrity, and availability triad. Secrets such as passwords, API keys, database connection strings, and private certificates must never be committed to a Git repository, even in a private one. Once a secret is committed, it exists in the Git history and can be recovered even if the file is later deleted. Correcting a committed secret is not as simple as deleting the file. You must rewrite the Git history using tools such as Git filter branch or the BFG repo cleaner to erase the sensitive data from all past commits, then immediately change the compromised credential in the target system. Branch protection policies prevent direct pushes to critical branches such as the main or production branch. They require pull requests, code reviews, and passing automated checks before any code is merged. A concrete example. A developer accidentally commits a file called config.m containing a database password. Even if they delete the file in the next commit, anyone with access to the repository can run git log and git show to retrieve the password from the previous commit. This is why pre-commit hooks are essential. Pre-commit hooks. The first automated security gate. A pre-commit hook is a script that runs automatically on the developer's machine before a commit is finalized. It acts as the very first automated security checkpoint in the pipeline. A minimal pre-commit configuration should at least scan for secrets and credentials using tools such as Detect Secrets or Trufflehog. These tools look for patterns that match API keys, tokens, passwords, and other sensitive strings. Check for obvious syntax errors or forbidden file types. Reject the commit if any violation is detected, forcing the developer to resolve the issue before the code can enter the repository. Pre-commit hooks can be set up using the pre-commit framework, which allows you to declare rules in a simple configuration file called pre-commit-config.yaml. The hook runs locally, meaning problems are caught before they ever reach the remote repository. Important limitation to keep in mind: pre-commit hooks only run on the developer's machine and can technically be bypassed using the no-verify flag. This is why pre-commit hooks are the first gate, not the only gate. They must be combined with server-side controls and automated pipeline checks. Static application security testing. Analyzing code without running IT. Static application security testing refers to the practice of analyzing source code or compiled binaries to detect security vulnerabilities without executing the application. It is typically integrated into the continuous integration stage of the pipeline, meaning it runs automatically every time new code is pushed to the repository. Examples of what static application security testing tools look for. SQL injection patterns, where user input is directly concatenated into database queries. Hard-coded credentials left in the source code. Use of deprecated or insecure functions. Missing input validation or output encoding. Popular static application security testing tools include SemGrep, SonarQube, Bandit, for Python, and ESLint with security plugins, for JavaScript. These tools produce reports that highlight the file, line number, and nature of each detected issue. Software composition analysis, securing your dependencies. Modern applications are rarely built from scratch. They rely heavily on third-party libraries and open-source components. Software composition analysis is the practice of automatically inventorying these dependencies and checking them against databases of known vulnerabilities. For example, If your Python application uses an older version of the requests library that contains a known security flaw, a software composition analysis tool will flag it and recommend upgrading to a patched version. Tools commonly used for software composition analysis include a WASP dependency check, SNIKE, and GitHub's built-in Dependabot alerts. These tools are integrated into the pipeline and run automatically on every build, ensuring that newly disclosed vulnerabilities and dependencies are detected quickly. Dynamic application security testing. Testing the running application. Unlike static application security testing, dynamic application security testing involves testing the application while it is actually running. The tool sends real requests to the application and analyzes the responses to detect vulnerabilities such as cross-site scripting, SQL injection, authentication weaknesses, and insecure configurations. Dynamic application security testing is typically run in a staging environment, which is a copy of the production environment used for testing purposes. It should never be run directly against a production system without explicit authorization, as it can cause disruptions. A well-known open-source tool for dynamic application security testing is a WASP ZAP, Z-Attack proxy, which can be integrated into a pipeline to run automated scans after each deployment to the staging environment. The minimal secure pipeline, a step-by-step summary. Here is the minimal sequence that constitutes a secure pipeline, combining everything covered above. 1. Developer writes code locally. 2. Pre-commit hook runs automatically before the commit is saved. It scans for secrets, checks syntax, and blocks the commit if problems are found. The commit is pushed to the remote Git repository pot 4. Branch protection rules ensure that the code cannot be merged directly into the main branch without a pull request and at least one code review pot 5. The continuous integration pipeline is triggered automatically upon the pull request. Static application security testing scans the source code for vulnerabilities. Software composition analysis checks all dependencies for known vulnerabilities. Automated unit and integration tests run to verify functional correctness. 6. If all checks pass, the code is merged into the main branch. 7. The continuous deployment pipeline deploys the application to the staging environment. 8. Dynamic application security testing runs automated security scans against the deployed staging application. If the dynamic application security testing scan passes, the application can be promoted to the production environment. Monitoring and logging continue in production to detect anomalies and potential incidents in real time. Key security concepts to remember. Confidentiality means ensuring that sensitive information is accessible only to those who are authorized to see it. In a pipeline context, this means protecting secrets, restricting access to repositories and deployment environments, and encrypting sensitive data. Integrity means ensuring that data and code have not been altered in an unauthorized or unexpected way. Git commits, checksums, and signed releases all contribute to integrity. Availability means ensuring that systems and pipelines remain operational and accessible when needed. This includes resilient infrastructure, automated recovery mechanisms, and protection against denial of service attacks. The concept of a threat in the pipeline context refers to any actor, action, or condition that could exploit a vulnerability to cause harm. Common threats include a malicious insider committing backdoor code, an external attacker exploiting a vulnerable dependency, or a developer accidentally leaking credentials. Important rules to memorize. Never store secrets in Git. Use dedicated secret management tools such as HashiCorp Vault or environment variables injected at runtime. Always enforce branch protection on the main and production branches. Run static application security testing and software composition analysis on every pull request, not just periodically. Dynamic application security testing must always be run on a non-production environment. A pre-commit hook is useful but not sufficient on its own. It must be part of a layered security approach. Rotate any credential that has been exposed, even if you believe no one saw it. Document all security checks in the pipeline configuration files so they are versioned and auditable alongside the code. This memo sheet is your reference card for the minimal secure pipeline. Revisit it regularly as you progress through the course, and use it as a checklist when setting up real-world pipelines in your professional projects.